Hello, this is going to be a continuation of my series on the Rayleigh Criterion and the angular compression. I've already made two videos. I'm going to link the first video in a card right about here and the second one right about here. And the second one was actually part 1.5, which was really a follow-up to a comment I got from part number 1. And I was asked to address what happens when you change the exposure. And so in the second part video, I bracketed the camera at different stops so that you could see what kind of effect that would have on the Rayleigh Criterion, or if it would have any effect at all. As a quick summary, I didn't do that in the second video, but all of the images that I took, I made available. So you can go in the description link of those videos and it'll take you to a link to my Google Drive that contains the zip files. In this one here, I was using my Nikkor 18 to 105 millimeter zoom lens. It was at 62 millimeters. I had the f-stop at 36. And it was 1/64th of a second with an exposure compensation of -5. And so I just duplicated this layer so that you can see the before and after, but you can almost barely see where the gray part kind of is all blended together, and you can kind of more or less see where the edge is here. But what I'm going to do is I'm going to play around with the brightness contrast level so you can kind of see where things are. So if I kind of crank these up more or less to a reasonable exposure level, you can kind of see where it is. And on my screen, it's right around here where you can kind of get a feeling for the outline. And if I look at this layer here, this one's going to be closer to properly exposed, and the level is about the same. So I just wanted to point this out. And that would kind of make sense that the aperture size, or the f-stop, that a particular lens is capable of going down to will get to the point where the Rayleigh Criterion just starts to kick in. So in other words, if you close the iris of the lens down to the point where you start to lose detail, there's not much point in going much farther. It didn't quite click why certain lenses on certain cameras had to be so large relative to others, but it does kind of make sense that the overall diameter of the lens determines the amount of light that gets let in, and a larger diameter lens would therefore focus more light into the camera and allow for faster shutter speeds, etc. And so just to compare several lenses, this isn't the exact lens that I was using. I was using the 18 to 105, but this is just to show that different lenses have different filter sizes. So this is the screw-on threads on the end of the lens that will allow you to put on external filters. And so this lens here, the 18 to 55, has a filter size of 52 millimeters. And the 70 to 300 has a filter size of 58 millimeters. So when this lens is zoomed in to 300 millimeters, in order for the camera to capture the same amount of light, or similar amount of light zoomed in at that level, the lens itself has to be larger to capture more light. And so the iris is kind of tied to the focal length of the lens and the diameter of the outside of the lens, such as this. And if I compare that with the P1000, it's got a 77 millimeter thread diameter for an external filter, and the P900, which is not capable of zooming in quite as much as the P1000, it's only got a 67 millimeter zoom. And so the first part of my video was to analyze the optical characteristics of the lens and of the camera to the point where the light reaches the sensor. Because you could take the sensor from a $10,000 camera and put it behind a cheap $70 bargain store kind of lens, and it'll look like complete and utter garbage. Likewise, you can take a sensor from a point and shoot camera and put it behind a $10,000 lens, and it's still going to look like a $70 point and shoot camera. So part one was really to look at the optics of the camera to the point where the light hit the sensor. So now in this part, I want to look at the role of the sensor and how the light hitting the sensor comes into play. So since the focus of flat Earth tends to be on why ships seem to disappear bottom up first, I decided I was going to use the closest thing that I could find in the house to a ship. So I ended up digging out my old Radio Shack Sea Battle game that I had out of a box, and I then took various images. I set the camera up on a tripod and I started to zoom out, and as I started to zoom out, I wanted to see what effect that would have on the final image. So I took this GIMP project and I saved a copy of it, and then I cropped out the parts of the image that were not relevant. And here I'm zoomed in as far as I can go. And for each of the layers where I was zooming out, I measured the distance from this point of this toy ship to this point of this toy ship. Here you can see I got 907 pixels. And in the next layer down, I took the same reading, got a scale factor, and then I scaled those layers to match the first one. I didn't try to get it exactly, but you'll see shortly that everything seems to line up fairly well. I lined it up on this hole that you would put one of the pegs in if that square got hit, and I lined it up on this little mast kind of thing for this battleship. So how does this look when you zoom in or out and then you rescale it? And just one more note, when I was rescaling it, I told it not to do any kind of dithering at all. I'm not going to actually scale it, but interpolation, it defaults to cubic, I believe, so I had to set it to none because I wanted to keep all of the pixels as they were when it got scaled up or scaled down. So you can see in this one here where I'm zoomed in as much as possible, you can see that there are ridge lines like this in this ship here. But as I start to zoom out, you can see that the detail is starting to get lost. And then finally, at the very end, you can't really see much detail at all. In fact, if I compare these two, you can see that this one says it looks like H7, but over here, all you see is a couple of pixels that are brighter than the other ones. You don't even know that this is an H7. So what I did to illustrate what's going on, and the point that I'm really trying to drive home, is that flat earthers will claim that it's due to angular compression, and when you zoom in, you're able to see more detail. And that's really a bit of a logical fallacy because that assumes that the camera is able to see all of the detail that could possibly be seen zoomed out, and that the angular compression outside of the camera is what's really causing the loss of detail. And this is a very crude representation of the camera, but what I've done is I've drawn the body of the camera, and here's the lens, and these alternating black and white squares represent pixels of the sensor. Here I've created a test pattern that you could point the camera towards, and they're both the same size. So I'm just going to move this down to the bottom of the screen so you can kind of see it's the same size here. And if I scroll down, you can see it's about the same size. So these two really are the same size. And when you're close to the camera, the light would go in this direction to hit this sensor. The light from this square would go in this direction to hit the sensor. So this is why this appears upside down. And here I've drawn where the focal point would be, and I've even put a marker here to show where that focal point would end up being. If we move away from the test subject and we do something similar, this is how it would end up appearing on the sensor. And you can see that the focal point is over here now, and I have another point over here that shows the focal point. So whereas this one might have been, let's say, maybe 30 millimeters, this one might be 40 millimeters. And there's a couple of pixels over here that are not in play at all looking at this object, so the object will appear to be smaller in the image, and so I'm going to take those extra pixels out of the picture. So what I've done here was just to show a partial set of colors hitting these individual pixels. So here's those pixels that come into play, and when the light strikes them, I just skipped every second one here, and I've got a couple of extra layers. So in this one, I combined the black and the white, so now it's going to appear to be a slightly darker gray. This one's going to appear a slightly different green than this one. This one's going to be a slightly grayer looking blue. This one's going to be more magenta color than these two, etc. And then whenever I finally add the last one, this should be how it gets represented in the image. And I say this is how it should be represented. And I just use 33% layer for this one, 33% opacity for this one, and then this one here is 100%. And whenever I combine the three together, that is how GIMP interpreted the colors in the individual sensors like that. But basically, just like in a real photograph, if I were to take this higher resolution image and combine several of the pixels together to create a lower resolution image, you will simply lose detail. So once again, the camera itself is subject to the pixels registering different detail. If you have different detail, such as these lines striking the same pixel in the camera can only do an average of those two bits of detail. Thus, you end up losing the definition of the image. And once again, this has absolutely nothing to do with angular compression. All things considered, it is very much like old film photography when you use a higher speed film such as ISO 1600 and compare that to the detail that you can get from ISO 100. The finer grain of the emulsion in the ISO 100 will, by definition, produce a higher quality image showing more detail than the ISO 1600 film in the exact same camera with the exact same lens, because the grain in the film emulsion is much smaller in the ISO 100 film. In digital terms, it would be the equivalent of taking this sensor out of the exact same camera and putting in a different sensor that has a much higher pixel density. So imagine 1, 2, 3, 4, 5, 6 pixels replaced with a sensor that has 12 of them. So now you've got this pixel, which is able to register this one, and you've got a separate one, which is able to register this one. And so now the camera is suddenly able to see twice the amount of detail by doubling the pixels per unit length. That's going to be it for this one. If you like this video, I would certainly appreciate the thumbs up, the subscribe, the comment below, etc. You know what to do. And I'm going to see you again in another video soon enough. So bye for now.